In this video, we will do two practice problems from section 3.1, number 2 and number 19. So number 2, I wrote on your assignment that you can kind of disregard the directions here. This is using our old definition, which you're more than welcome to use, but we're going to use the new definition here. So this f of x is x squared plus 4, and we want to find the derivative at a, which a here is 1. So we basically want to find f prime of 1. That's our goal. And what we're going to do is use the definition to find f prime of x. We're going to use the definition of a derivative, which is the limit as h approaches 0 of f of x plus h minus f of x all over h. And we're going to say the limit again. Then we want to plug in x plus h, which will get squared, and then add 4, minus our original f of x, which we do need to put in parentheses since we're going to distribute the minus sign. Then to square x plus h, we use our trick, so it's x squared plus 2xh plus h squared. You'll start to know that by heart. Plus 4, then we'll distribute the minus sign through. At this point, everything that does not have an h in it should cancel out. So the positive x squared and the minus x squared, positive 4 and negative 4 all cancel out. Then we only have terms that have h in them in our numerator, which we can factor out that h to get it to cancel with the h in the denominator. So we're left with 2x plus h all over h. The h's end up canceling, and then we can use direct substitution and plug in 0 for h. So that gives us just a 2x remaining. So in conclusion, f prime of x is 2x. Now our goal was to find f prime of 1. That was our ultimate goal. So f prime of 1, we plug in 1, and we get a final answer of 2. So the derivative of f of x equals x squared plus 4 when x is 1 is 2. Generally, the derivative anywhere on that function is 2 times the x value. Number 19 is asking us to find the equation of both the tangent line and the normal line to our function f of x equals x cubed at the coordinate point 1, 1. They gave us both the x and y of that coordinate point, which is great. So in our lesson video, I'm not going to do all this back work, but in our lesson video, we found that f prime of x for this function, x cubed, it was our first example we did. We did all the work and used the definition of derivative to find that the derivative of x cubed is 3x squared. So I'm not going to go back through that whole process. We did that in our lesson video. So we know that the derivative of x cubed at any point x is 3x squared. So again, to write the equation of a line, I'll do the tangent line in yellow, we need the slope and we need the point. The point is 1, 1, that's given. The slope when x is 1, is plugging into our derivative. Since the derivative equation gives us the instantaneous slope or instantaneous rate of change at any point. So f prime at 1 is 3 times 1 squared, which is just 3. So now we have the slope, 3, and the point, 1, 1. So writing the equation of the tangent line isn't too bad. It's going to be y minus 1 equals 3 times the quantity x minus 1, which is point slope form. So we have 3x minus 3. And then we add 1 to both sides, so we'll get 3x minus 2. That's our tangent line equation. The normal line equation, part B, is we are still going to use the same point, and again, we still need a point and a slope. It still passes through the same point. But recall from section 2.4 that the tangent line and the normal line are perpendicular, therefore their slopes are opposite reciprocals of one another. So since the slope of the tangent line when x is 1 is 3, the slope of the normal line when x is 1 is negative 1 over 3. That is the opposite reciprocal of 3. So we again use our point slope form, y minus 1, and the only thing different here is the m value. Then when we distribute that negative 1/3 through, we'll get negative 1/3 x plus 1/3, and then adding 1 to both sides, 1/3 plus 1 is 4/3. So this is the equation of our normal line. So the moral of the story is that the derivative function is your slope at any exact point. It gives you the instantaneous rate of change or the instantaneous slope at that point, which is the slope of the tangent line at that point.